Right, okay, good afternoon, and do apologize for a very slow start. It looks like YouTube has been very funny today with us, and now we are all live, and I'm very happy to introduce you to the great panel and speakers who will be presenting at the technical session 2 of our day. It will be focusing on the building safer and more efficient mining, and the session will be moderated by Tim McGurk, who is a corporate consultant, mining engineer for SRK Consulting. Microphone over to you, Tim. And I would like to remind everyone to use the the public chat on the broadcast page. If you have any questions for speakers, we'll send them over, and then if we have time at the end of the session, they will try to respond. Without further ado, Tim, microphone and camera over to you.
Thank you, Arthur. Yes, hello everybody, and welcome to our second technical session of today's discussions. We have a section here on building safer and more efficient mining, and I think it fits very well with the the climate that we're in now in terms of environmental and social governance, the climate change. Looking for energy efficiency and sustainability in mining, that being as efficient as we can, and of course providing safe operation, is incumbent on us in the industry to deliver the kind of mining environment and support for the industry and economic growth. So we've got 6 speakers for this afternoon, some of whom I know, SRK colleagues, and some who I haven't met, but well, I'll introduce them as we go. We're going to start with William Harding, who's a principal hydrogeological consultant with SRK, and he's talking with Mike Di Giovanzano, who is a principal geotechnical engineer also with SRK, and they're going to be discussing the collection of technical data during the exploration stage of the mining cycle. So I'm going to hand over to you, William. I think you're going to kick off, and yeah, we look forward to it. Thank you.
Thank you. Right, let me know if you can see.
Yeah, please carry on, William. Yeah.
Good afternoon, everyone. Today, Michael Giovinazzo and I will be giving a short presentation on how one can piggyback hydrogeological and geotechnical information on the back of resource and infill drilling programs, effectively to bring project owners more value in terms of early information in the project, and also obviously saving money as well. So the background to this is that we're very conscious that resource and infill drilling programs to support exploration studies entail a lot of drilling over the course of some years. Sometimes on the bigger projects, we're talking about tens of kilometers of drilling. And when you reflect on the fact that those costs are typically 150 to 200 euros per meter, you can accrue a considerable amount of expenditure over several years. And this begs the question, well, if at the end of that you have a resource but not much else, is there an opportunity for other disciplines to piggyback on the resource program to bring extra value to the project? And this talk is essentially describing how one can build other disciplines into a resource program. So what normally happens with a resource drilling program? You have a series of boreholes, drill hole planning, the rigs attended and the drilling contractors attended for. There's a mobilization, and then holes are drilled, core is photographed, logged, and then cut and sent off for assay. There then follows an economic evaluation of the ore body based on the results of the drilling. And it's really only at that stage that questions start to get asked about, well, if we have a viable project here, we should be thinking about acquiring information to support other disciplines that will go towards, producing a project-ready mining study. But in reality, what we find is that by the time the geotech and hydro and other disciplines come into the picture, and questions start to get asked about, well, what's known about the groundwater system, what's known about the rock mechanics, and usually the data is fairly incomplete. It's not a very good quality, so increasingly what we found is that if one can piggyback onto a resource drilling program, you overcome a lot of the shortcomings of what historically tended to be just focused on a resource evaluation. So on this slide here, we're basically summarizing where the advantages are in piggybacking. The most obvious one is that if you can do your hydrogeological testing and geotechnical testing on resource drilling holes, then you don't have to double up on the drilling. You save capital, you reduce the logistical burden, and of course you bring forward information that will be useful to inform the project. There are all sorts of other benefits. I'm conscious that environmental studies rely on having a good set of baseline data, and the longer the period of data capture, the better. So one of the things that can be done on a resource drilling program is to set up the baseline data capture. So I won't go into too much detail about the definition of piggybacking. It's essentially just bolting on extra work to another program. But in order to integrate and adapt hydro and geotech testing work, we need first of all to understand what the challenges are that we need to overcome. Key amongst those is the drilling schedule. There have been a number of projects that we've been involved with in over recent years where it's very time sensitive, and so it's critical that whatever testing is designed fits into the resource drilling program where the priorities are to support an evaluation of the ore body. There are other aspects. So from a geotechnical point of view, most resource holes tend to be of limited, in terms of orientation, a limited number of orientations. For a geotech study, you want to vary that orientation to give you some 3D information. And then there are other aspects like adapting to a reduced hole diameter, which impacts particularly on groundwater investigations. And then, of course, there's also core handling. From a geotechnical point of view, the emphasis is on retaining and capturing as much information from undisturbed core, whereas a typical resource drilling program, there may be a lot of handling, and then there's this core splitting. And of course, if that's done before the geotechnical information is captured, the value of any geotechnical study on the resource drilling is greatly diminished. So how can we design a piggyback testing program to fit into an exploration drilling program? And you can see a typical flow diagram at the bottom of the screen there, where you can see how we can adapt geotech and hydro studies. Simpler, less sophisticated studies we can introduce early on in the exploration, and as the owner's confidence in the project increases, then we can increase the complexity and the sophistication of the hydrogeological and geotechnical testing techniques. There's a box on the right of this screen. This essentially summarizes what I'm going to cover in the next 3 slides. Essentially, I'm going to focus initially on test design. Then we're going to look at how we can adapt the tests to limit cost, and how we can moderate the test design so it's less or more sophisticated. And then I'm going to talk a little bit about integrating testing into a drilling schedule. So from a hydro point of view, over a number of years, we found that actually you can adapt most hydrogeological techniques to resource and infill drilling programs. It's just a case of the level of sophistication, how you can adapt techniques to fit a much reduced hole size. And the same applies to geotechnical data capture as well. So here I'm just going to talk about testing techniques very briefly. I'm going to pick out a few examples to illustrate, but these are very typically hydrogeological testing and geotechnical testing techniques that we would utilize on the back of a resource drilling program. So if I touch on packer testing, first thing I can say is that there is packer testing equipment out there that can fit in NQ and HQ holes, which is fairly critical from a resource point of view, because most resource holes really operate within the BQ to HQ size spectrum, which is essentially 60 mil up to 100 mil. The packer testing is also it's also important to emphasize that the packer testing technique is one that integrates well with the drilling program. You can actually drill an interval, run the clean up, flush the hole, and run the packer in, test 50 meters or whatever that interval that's been drilled, pull the packer out, drill another 50 meters, and repeat the exercise with the packer, and you can run it all the way down the hole that way. Or you can come in afterwards with a straddle packer, which is paired packer, and target specific structures after the resource drilling is complete. So the emphasis there is flexibility and hole size. But what you notice there is that we're having to use a rig to operate a packer. At the other end of the spectrum, we can build in monitoring wells that don't require a rig to sit over the hole, using fairly cheap materials, and likewise, we can go in and develop and do geophysical and flow logging. Again, no rig over the hole. These things are done after the resource drilling rig has moved off the hole. Lastly, there's a vibrating wire pressure transducers, which are rather more sophisticated than standard standpipe holes. But again, you can see we need, because of the weight of the equipment, we need a rig, and because we need to do grouting and various other things, it's better to have a rig over the hole. So I'm hoping that I've demonstrated that there are different levels of sophistication, and there are some forms of test that require rigs and some we can get away without. The next point I wanted to talk about was how you can, based on the sophistication of the testing, you can control cost and time. So for early stage exploration, you want to have a fairly unsophisticated, simple form of testing. But as you move into the later infill drilling, then you can use more sophisticated tests, such as packer testing or vibrating wire piezometers. The next one, what's really critical from a resource drilling program point of view, and I've touched on it already, is the need to not impinge too much on the resource drilling schedule. And the two examples I have here on the screen are based on actual time pressure drilling programs, where we've worked with the project owner and the geologists on the team to develop different techniques to limit the amount of time, for example, that the resource rig is on the hole. If we, for example, were to use flow logging and smart well technology on the hole, there would be no delay to the resource rig. Alternatively, if you wanted to do something more sophisticated and use packers or vibrating wire piezometers, the rig would be on the hole for longer. That would obviously delay the program a bit, but the quality of the information you get out of it is better. Michael, can I pass over to you, and you can perhaps chat very briefly about the geotechnical characterization and how we can adapt that.
Thank you, William. Most of what William has mentioned regarding the hydrogeological testing is related to the drill hole and during the drilling phase. From a geotechnical point of view, a lot of data can be collected in the early stages of the logging program for quite a little bit less time than maybe thought what a geotechnical logging program may entail. Usually, fractures are counted and an RQD, rock quality designation, is determined in most programs, but by collecting another 3 parameters, you can get close to achieving one of the rock mass classification systems in your very early studies. So by increasing the amount of data you have early on and leading into further study stages when you're embarking on a mining assessment, you have a good baseline of geotechnical understanding, which gives you a good sense of the expected ground conditions that will lead into the possible mining methods, the risks associated with that mining method in the early studies, as well as that by gathering some simple strength testing data. It can also inform the metallurgical processes involving crushing, so the rock strength change along the deposit, the blastability, the rock cutting requirements if those type of tools are implemented. So as I've got down the bottom of the table on the bottom row, 10 to 20% extra logging time using the same geological team that you are logging the geology and the structural geology with, you can achieve a geotechnical baseline data set. For interest further into the study, there is extra time required in logging, so another 50% extra time will achieve the full set of rock mass characterization, logging, and therefore analysis. And further down the line, you can employ geophysical techniques like what William is talking about, and actually scanning the borehole wall, which further defines what ground conditions you'll interact. Just the next slide, William. That's just giving some images to the type of data collection that I've been talking about there. The 6 parameters that are in the table can pretty much calculate any common rock mass classification system that is used in the industry. But what is paramount is that there's a high percentage of oriented core, which is very important from a resource definition point of view anyway, because structural geology controls everything. So with oriented core, you can get a good feel for the 3D understanding of the fabric of the rock mass. And as well as that, using a point load testing instrument, which is a portable hydraulic press, you can compress core samples to get a good database of rock strength index testing that is done. And on the right-hand side there, by drilling in different orientations, it's a no-brainer. You are sampling the rock in a 3D sense and getting a good 3D understanding of the fabric of that rock mass. Thank you, William.
So we're going to wrap up now. I just wanted to show a few examples of, or several examples of projects that have been completed in Northern Europe and Western Europe, in Africa and Latin America over recent years, where the project owner has carried out exactly what we've been describing in this presentation. They've essentially piggybacked hydro and geotechnical testing onto their resource and infill drilling program to great effect. And so thank you very much for listening. Really going to summarize here in a few lines the benefits of piggyback testing. It saves money at the end of the day, it saves time, and it gives the project owner, the management, an improved holistic or overall understanding of the issues that the project is likely to be faced with at an early stage. This de-risking of the project means that they are able to do better planning, both in terms of decision making about the way forward on the project, but also to help design their technical studies going forward.
Okay.
Okay, thank you.
Yeah, thank you very much, William. It was very good, very interesting. Okay, we'll move on to our second presentation. Chris Bray is a principal mining engineer with SRK in the UK, and Chris is going to discuss planning for the use of battery electric equipment in underground operations. So something that we're seeing a lot of interest in, and I think will be of interest to quite a lot of people. So over to you, Chris. Thanks.
Okay, thanks for the introduction there, Tim. Is the slides coming up okay? Okay, so I would like to introduce you to some of our team's experience in planning for battery electric equipment in underground mines, where we continue to develop our capabilities with the progressing technologies in order to support mining companies. Battery electric technology is increasingly being considered by mining companies as an alternative to conventional diesel power for underground mobile mining equipment. And the SRK Group continues to develop and support mining companies in assessing the potential for battery electric equipment with mine planning, ventilation, cost estimation, and simulation capabilities. SRK is an employee-owned independent consulting group with recent battery electric experience on projects and operating mines, including the Nordic region, up to a feasibility level. A benefit of battery electric over diesel equipment is a significant improvement in the efficiency and reduction of heat generated by the mobile equipment. These figures are sourced from the Global Mining Guidelines Group, and the upper figure compares the efficiency of each component of the respective electrical and diesel motor drives and the respective heat losses. Heat generation for battery electric equipment is reported to be as low as 20% of similar diesel equipment. The lower figure shows the comparative energy flow when a truck is hauling up a ramp. The battery electric truck is able to charge up the battery through downhill tramming and regenerative braking. There are limitations to the energy storage capacity of batteries and the cost of the battery itself. However, these aspects are anticipated to improve over time. A future opportunity for longer hauls will be the combination of battery electric and trolley assist power sources. So this slide provides some examples of battery electric developments with equipment suppliers, mining companies, and contractors over just the last 2 years. It should be noted that the Kirkland Lake Macassa mine started using battery electric equipment back in 2012, and reports now indicate that it is using the technology for more than 80% of its ore production. Battery electric equipment options continue to increase through equipment providers, and factors such as equipment capacity, battery charging time are also improving as the technology continues to develop. Some of the key considerations are shown for planning an electric mine. There are many material factors to consider, both positive and negative, for individual projects. For certain aspects, such as materials handling, there may be fundamentally different approaches required for designing a battery electric mine. Additional considerations are required to determine the preferred charging approach and the location of charging infrastructure to achieve the required production rates. How do we capture these options in a mine plan? We break it all down and use the planning tools at our disposal. One of the most positive benefits from an electric mine is the improved air quality, which reduces the ventilation infrastructure requirements and includes smaller or less ventilation raisers and fans. Ventilation requirements for diesel equipment is primarily driven by the combined engine power operating at any period, while electric equipment ventilation is more driven by minimum air velocities to manage heat, dust, and personnel underground. Emissions are significantly reduced as indicated by the comparative example table, showing the contribution from equipment and blasting activities to emissions from the mine for both a diesel mine case and an electric mine case. The project economics are one of the primary drivers for a mine deciding to go down the path of battery electric technology. And the example shown here is for a battery leasing arrangement. The capital costs for electrical infrastructure can be minor in the big picture for developing a new underground project. Operating costs are heavily dependent on the cost of battery leasing, diesel, and power consumption. Material cost savings can be achieved for reduced maintenance labour and wear parts for battery electric equipment. This was the fancy simulation slide I was hoping to show, but anyhow, you can use your imagination. Simulation is an appropriate planning tool to optimize the mining layout and provide more confidence in the equipment productivity estimates. This example shows how mine planning can be taken to the next level in a dynamic simulation environment to capture opportunities for recharging equipment and ensure that sufficient development and infrastructure is in place to achieve productivity targets. The Global Mining Guidelines Group, or GMG, it is well known, is a global community including experts from mining companies, equipment and technology providers, and consultants. GMG is focused on advancing the availability and use of standards and guidelines for developing technologies such as battery electric equipment for the international mining industry. A recent survey undertaken by the group provided some useful results to consider when progressing towards an electric mine, including the information which provides the most value, and equipment and alternative sources of power which are considered a priority. If you are interested in the full survey results, a link is provided at the bottom of the slide for following up. So every project on assessing battery electric equipment for underground mines provides new learning outcomes, as we've found out. I'd recommend that where possible, battery electric considerations are assessed early in the project to develop an understanding of the mine design, requirements for charging, and estimates of costs. Detailed planning must be considered for shift structures and charging opportunities for the equipment. And in conclusion, proper planning and trade-off assessment is required to understand the opportunities for battery electric equipment. The technology for battery electric equipment continues to evolve with improving cost and productivity considerations. SRK values external support from specialist electrical engineering groups such as Bestech, and certainly appreciates the ongoing contributions from equipment suppliers. SRK also continues to work with universities and support graduate research projects on the assessment of developing battery electric technologies. And just to finish off, if you do want to follow up, this is the location of our offices around the world. Please get in touch and we'll be happy to assist. And following that, there's our standard disclaimer. So thanks for your attention and enjoy the rest of this session.
Thanks very much, Chris. And we didn't get to see the trucks running around on the animation, but next time.
I was so looking forward to that.
All right. Okay. No, it's good. And obviously, we're seeing battery technology developing and increasing confidence with the technology, increasing levels of knowledge as well, supporting organizations and companies to make their decisions around that technology. Okay, so next up is Andy Beveridge. Andy is a senior engineer with Patterson and Cook, based in the UK, and Andy is going to talk to us today about the benefits of backfill in mines and what that can bring. Okay, so Andy, over to you.
Thank you. Can you hear me okay?
I can hear you fine, yeah, thanks.
Excellent. Right, yes, today I'm going to have a quick presentation here on some of the benefits and opportunities associated with mine backfill. Okay, part of this, I'll be discussing the current surface disposal approaches, some of the restrictions associated with surface disposal, how we can capitalise on the void resource, a brief overview of some of the common descriptions for disposal, and a bit of a chat about the underground backfill plants. Okay, so for surface storage, we generally have two main methods for waste material. We've got rock dumps and we've got the TSF, the tailings storage facility. So TSF, we've got wet and dry facilities, and the wet facility generally takes a tailings slurry from the process plant, deposits it in a large-scale pond where it dewaters and the like. Apart from the operational issues, you've got long-term factors with these TSFs. You've got to maintain the drainage post-closure, liquefaction risk, erosion, stability, and the like. There's a large surface area associated with this, so the land demand can be quite high, and that could be an issue in certain sites. You may have height limitations. We know about the high-profile failures that have occurred, so I won't go on about that. But that leads on to your social license to operate. You know, an understanding that you need to behave responsibly and demonstrate that you're performing as best practice and you're doing the best you can do. There's been a bit more of a drive in the past few years towards dry stack of tailings. The idea being you pressure filter the tails, return the water back to process, and then dry stack and compact your tailings. Not all tailings are suitable for this, so in some cases it's still viable to stick with your wet tails facilities. The other common type of waste rock disposal on surface will be rock dumps, where you stack your waste rock on surface. Your operational profile will differ to your long-term post-closure profile. As for post-closure, you'll have to lay back to stable angles on the batters. You'd be looking at re-vegging the profiles, and in some cases you might have planning constraints which dictate you have to restore to your pre-mining conditions. As far as surface restrictions and planning and environmental constrictions, just a quick slide here to demonstrate a mine which is looking to restart, which are quite constrained. They've got a very limited footprint. They're surrounded by industrial sites. They're in a World Heritage Zone. They've got urban areas. They've got plenty of underground workings as well. So this restricts what you can do on surface, but it also gives an opportunity to stow material in the underground environment. What we're talking about here is the void as a resource and treating it as an asset rather than just a depleted area of mining. So what we're proposing here is, instead of stacking material on surface, consider putting what you can into the old workings. So whether that's surface or underground. So there are potentials to stow waste below surface. This might be like at the bottom of the slide there is an open pit. And in the space of 10 years, that was backfilled with tailings. Now, clearly not every pit is appropriate for that, but there was an opportunity there. Part of this is to, reduce the volume of material stored above surface. But there's also opportunities to stabilize existing openings and manage stability of the long-term stability of old pits, and try and help to reduce or eliminate geotechnical hazards. As far as the open pit void resource, typically these are rock filled, but as per the previous slide, you can tailings fill in certain situations. You can use a rock fill to help mitigate against future stability issues by, in the example below, buttressing a failure, but also using the waste rock instead of surface storage into the old open pit here to help restore the mining profile to the sort of the pre-mining state, dispose of material in the subsurface environment, and stabilize the workings. A little note I should add there, of course, is in-pit disposal of waste, whether it's in a live pit or in a dead pit, you need to be absolutely positive that you're not going back in there again. Because if you try and do this in a pit that's marginally below cutoff, as several operators have done in the past, you will sterilise your resource or incur significant costs to get back in there. A brief overview of underground backfilling methods, just for those that aren't aware. So starting in its simplest form, we're talking about rock fill. So we're taking development waste in the underground environment and placing that inside an abandoned stope or a disused stope. This is suitable in areas where the backfill won't be exposed again, but if you plan to mine adjacent to it, you need to bear in mind that waste material may fill in. So in many cases, but not all, it's not a viable method if you need to expose beside it. So the next method would be CRF, cemented rock fill, where you take your waste rock, crush and grade, combine with a binder, typically a cement, Portland cement, and then place in the stope. In this case, you can design in some strength so that the backfill can be freestanding, which enables you to expose vertically and in some cases undercut the backfill. Next up is a cemented hydraulic fill, and this would take a tailings stream. Typically, you need to modify the stream and take a coarse cut, whether that's a bank of hydrocyclones or something to arrive at that. But you then combine the coarse tailings with a cement and place underground. Again, you are looking to develop a backfill column which you can expose horizontally and vertically. But one of the side effects of this, of course, is you've got additional water going into the water balance within the mine. You've also still got the ultrafines on surface from the cyclone overflow. But you can produce a stable fill with that. And quite commonly now we're seeing paste fill. Again, it's a hydraulically transported method, and we tend to try and take the whole stream tails if the tails are suitable. Combine it with a cement again, and you can engineer a product which you can expose vertically and horizontally. There are a few bespoke options besides. There's a few combinations of the previous options, but an example here that I put of a bespoke system might be taking a cyanide sludge or some kind of horribly contaminated material, which you can combine with a cement, take underground as a block, and store indefinitely in the underground environment rather than surface. You can maximize your resource with the aid of backfill. So as well as the environmental benefits above ground, you can look at trying to increase extraction. So a common mining method you may encounter in an underground setting might be leaving pillars for stability and to manage the hydraulic radius. What you can do in some settings is you can actually you can backfill in cycles. So you mine, backfill, mine adjacent, backfill, and so on, and largely eliminate the requirement for pillars. Now this is case dependent on many things, but you do have potential to reduce the amount of ore you leave sterilized in pillars. There are other sequences you can look at. There's primary, secondary stoping, as shown at the bottom there, where you take your primaries, in this example as a CRF, and the secondaries could be taken as a CRF or a rock fill. In the case below, we were talking with a client about a rock fill, and they were modifying the mining system so that they could have an uncemented rock fill and basically advance that as they retreat the ore. So they were prepared to wire a bit of dilution for cost savings in the binder. So it's a modification of a Voca. One of the biggest drivers in backfilling, if you want to place your material underground, is your material balance. There's no point in having the perfect material if you haven't got enough of it. You need to understand what you have throughout the mine life, when you have it, and when you can place it. Typically, we look at the in situ ore volume that's mined in a year versus a backfill volume that's required, and check that you've got the balance between waste material and void space. You've got to bear in mind with that if you have to cyclone your material, you're going to be leaving fines on surface, ultrafines on surface in the case of hydraulic fill. So all of this needs to be taken into account in the mass balance and the material balance. You also need to consider things such as the addition of water to the underground mine. When you consider your cost trade-offs, clearly there's the TSF cost you might be able to trade off, closure costs, post-closure costs. There's also the risk profile, surface limitations, planning restrictions and the like, all of which need to be considered and are not necessarily tangible at the outset. You need to take a view on certain things. As far as CapEx and OpEx, you'll find that waste rock is generally the cheapest. And not always, but you'll find that the capital associated with paste can be the largest, and in many cases a hydraulic fill operating cost can be fairly high, mainly due to the cement volumes you need. There's been a bit of a driver in certain mines to look at planning for an underground plant. Again, trying to reduce surface footprints and keep what material you can underground. With the underground plant comes an underground backfill requirement. So if you can get the backfill plant underground at the same time, or even get the backfill plant underground regardless, you can save on haulage, you can save on reticulation costs in the case of paste fill, you can try and manage your pumping costs, material haulage. If you can reduce material going to surface, that's a good thing. Bear in mind with that though, you're going to have to stockpile raw materials underground. So even if you can keep everything underground, you're still going to be hauling cement in, for example, and you may need to silo or stockpile various forms of rock fill. Underground plant designs, the process is generally the same as surface. You design your process, but the layout differs. So it depends on your rock mass, what chambers you can manage, what stability you can manage. But what we're looking at generally is trying to cascade the material from top down. So you have your raw materials feeding at the top, vertical connections where you may be doing the mixing, as in this example, then off to some backfill pumps. That's the same general layout as we'd apply in a backfill plant anywhere on surface, but you are constrained by the rock mass and being underground. A couple of major considerations there are maintenance, being able to get in there to maintain the equipment, so you need to plan around that, but also stockpiling raw materials. So if you're bringing binder in, you need storage facility. If you are feeding in an aggregate, you may need an aggregate silo blasted into the rock or something. But all of these, and of course you've got your extra demand on your power system underground, but all of these things need to be considered from the outset. Okay, now in conclusion, and to summarize here, backfill is typically considered for mine stability, but it's increasingly becoming considered by clients for waste disposal to minimize surface waste. Apart from the direct cost, you're also looking at savings and opportunities associated with permitting in the environment. Common fills underground would be rock fill, cemented rock fill, hydraulic, paste fill, and several variants of the above. And different backfills are appropriate for different mining methods. That said, you need to understand your material balance for your life of mine before you go ahead and say, I don't know, paste fill's awesome, but it turns out you don't have enough of it. You need to plan around this from the outset. So the whole backfill considerations need to be made right from the start of planning. You can reduce your surface footprint by bringing your plant underground. Again, there's a lot of constraints on that, but it's an option we've looked at for several operations, and it's certainly with CRF and the like, it's applied around the world in different settings. You can use off-the-shelf plant designs. Again, it gets a little more complex underground because you have to fit in around your workings. So very often you find the underground becomes a little bit more bespoke and it's more of a stick-built plant. And ultimately, backfilling tends to be appropriate in open pit and underground environments. Not always, but very often you can find that backfilling is of benefit from the environmental side, from the surface storage side, and from the mine stability perspective. So yeah, thank you very much.
Thank you, Andy. That was great. Very clearly the environmental benefits coming through there on the use of backfill, as well as the more traditional trade-off of maximising resource recovery and balancing that against mine costs. So good to see that those things are coming through to the fore.
Good. Thank you.
Thanks. Okay, our next speaker, our next presentation is from Pavel Bartak. Pavel is a mechanical engineer with Howdens, the fan and ventilation suppliers. And Paul's going to be talking to us about VentSim control, ventilation on demand, and I guess how we can reap the benefits of this new technology in our mining operations. So over to you, Pavel. Thank you.
Okay, thanks very much. My name is Pavel Bartak. I'm with Howden VentSim Solution. Today I will be presenting to you VentSim Control, which is a ventilation simulation tool and a live SCADA for ventilation control. So let's go a little bit into a bit of background here. So what is the difference between ventilation on demand and ventilation optimization? So in ventilation optimization, some examples are running your fan speed at a manual setting remotely, synchronizing two fans to run at the same speed, having a gas sensor open automatically a door, or having flow measurements adjusting a regulator on the ground, or having a scheduled event that can open an airflow regulator on the ground. And then there's ventilation on demand as well, which is a type of ventilation optimization. So what is ventilation on demand? It's an automatic calculation of the airflow demand based on vehicle and personal presence. So how does VOD work? We're using the mine's ventilation existing infrastructure, and we gather the vehicle positions, personnel positions, the airflows, gas sensors, and then we send that to a VentSim control, which in turn takes the calculated values, determines the necessary fans and the regulator positions, and sends that information to the hardware, where the PLCs and the remote IOs enable the remote control of the equipment, such as fan starters, VFDs, and actuators. So with VentSim control, you can maximize production. So there's different levels of optimization. And one of them is being able to clear the gases faster, to be able to get the workers in their zone faster. Then we have asset management, which optimizes the fresh air use, which gives more capacity and flexibility to the vehicle fleet. The second aspect is improving safety, which is very important. Firstly is to improve the air quality. And then there's a whole system of managing different types of alarms. And we're logging all the system changes, and we assure the compliance monitoring for safety regulations. The third aspect is energy savings. So again, we have different levels of optimization. We always meet the airflow demands, but we reduce the amount of wasted air, which in turn reduces the energy fan consumption. And we have advanced controls for the operation optimization of fans and regulators. These generally get between 10 and 50% energy savings. There are some additional cost savings, such as peak electricity or the required air heating and cooling based on a reduced airflow into the mine. Let's look at the 5 levels of control. So there's level 1, which is manual remote control. Level 2 is automatic scheduling based on events. Level 3 is automatic flow control with also gas biases that can be enabled. Level 4 is ventilation on demand with tracking. And level 5 is optimization algorithms such as feed optimizer, total demand, or custom controls. So let's have a look at the VentSim control software. I'll show you a quick demo here. So here we have a summary page where we're seeing all of the airflow regulator controllers and fan controllers. We can see which mode they're in, and you can customize these pages to see all of your ventilation infrastructure requirements. For example, you can also filter for VOD only elements, so you can quickly see what's going on the ventilation side in the mine. And directly from here, you can open the faceplates to be able to access the fan control. So you can set the different control modes and the operating conditions for that mine, for that fan. There's no way to visualize the ventilation infrastructure. So for example, here we have a 3D model which is done in Ventsim Design, which is a world-renowned ventilation simulation software. And we basically import that and run the Ventsim Design model into Ventsim Control to have simulation data at the same time as live instrumentation data. So the black boxes show live instrumentation data from, for example, this airflow regulator, and you can see the resulting simulation and real live data. So you can double click on these objects and access the faceplates to control that regulator or fan. Okay, so here we can see that we can have a simulation environment that can be used to design the ventilation control ahead of time. And then when we get into the live control, then you just switch over to have controlling live the fans and airflow regulators or doors. Okay, so here there's another way to access the information. So you can, for example, import the level plans, superimpose the controllers, and you can see the control information and control directly from the level plans. So there are, it's all done through a configuration process. There's no programming involved, so it's very easy to configure. There's a number of reports that can generate, energy report, all kinds of reports and logs that are automatically generated. Let me show you quickly the 5 levels of control. So for example, here for this fan controller, I have it in manual control. So if I set it to 50%, for example, I have automatically configured in background an alarm. So alarms can be acknowledged. And these alarms, if you don't have somebody looking at the system live, they can be sent to an email to basically alert somebody that there's something happening in the system. They can log in and take action. So, and once the alarm condition has been lifted, then the alarm disappears. So that's manual control. Flow control is basically controlling the flow set point. So if we change this to 20 meters cubed per second instead of 25, then the controller automatically adjusts based on the PID gains, which have been configured, the fan's speed to attain the desired flow set point. That was actually level 3. Level 2 control is the scheduling control. So for example, here I have a scheduling event that changes the fan speed of this fan to 70%. So right now around 61 or so. So I can schedule this event in time, or I can just start it automatically, and that will change the setting to that manual 70%. Okay. Another example of flow control is we can enable a gas bias. So a gas bias or temperature bias. So in a zone, for example, here we have carbon monoxide monitoring. We have a set point of 9. We're actually reading 10. So if I enable this gas bias, it's automatically going to increase the airflow into the zone to be able to flush these gases. And the same thing could be applied for temperatures. So if you have high temperatures conditions, then a temperature bias could increase automatically the airflow pressure coming in to bring down the temperature in that zone. Okay, and we have different trending and all kinds of information that can be displayed. The next level of control is level 4, which is the ventilation on demand and tracking control. So we can see here as an example, I have the tracking interface, which is usually fed by the tracking system. So Ekahau, Aeroscout, NewTrax, for doing some examples, are going to be automatically feeding the system on what vehicle is in which zone and how much air it requires. So we can see in this demand, we have 20 meters cubed per second. That's the requirement based on this one diesel truck that is on. So if I switch over to ventilation on demand on the controller, now we can see that the set point is coming from that local demand of 20, and the controller is automatically adjusting to meet that demand. Okay, and level 5, so there are a number of optimization algorithms that can be applied. I'll just show you one example, which is a fan speed optimizer. So for example, here I have one airflow one fan exhausting from 4 parallel levels. The fan is currently at 100%. Each of the levels has its own flow or ventilation on demand set point. So it's maintaining its flow set point or ventilation on demand set point. So that's its job. And the fan right now is 100%, so it's not optimized. So if I enable the optimization, so I'll turn on the speed optimizer, it'll automatically look at the airflow regulators that are associated to it, and to alleviate the restriction to be able to decrease automatically the fan speed. So we can see right now this airflow regulator, which is closest to 80% opening, which is our set point, is actually increasing gradually in opening. That's relieving the restriction, not on just this one, but all the other regulators as well. So the fan can automatically decrease in fan speed and optimize its energy consumption. Okay, so that's just a quick little introduction. Let me pursue with my slides. So let's have a quick look at the software-hardware integration. So there are basically 2 options for the ventilation on demand hardware. So we can use the mine's existing hardware, or we can also get the Howden Ventsim hardware. So there are some advantages of the Howden Ventsim hardware. There are off-the-shelf products which provide simplicity and compatibility. The Ventsim control is designed to take account of full capabilities over the hardware. The configuration is backed up and restored very easily and quickly. The hardware kits are pre-assembled before shipment, which reduces installation time on site, and there's no programming involved. So what is required to install on site? First, you need a communication network. So it could be Ethernet, Wi-Fi, LTE. Then we need to have the automation layer with PLCs, remote IOs, or the Howden hardware. Need a software license, which is based on the control level and number of devices that you're controlling. And you need 2 servers, one for the control and one for HMI. These could be also virtual servers, and then provide the training either at Howden or on-site. Additional on-site options are the system configuration can be done by us, or we can train the clients to do that. Same thing for the system commissioning. There's software maintenance that needs to be considered, and remote or on-site support that we can provide as well. So let's have a quick look at some case studies to have some real-world examples. So here we have the Fresnillo San Julián mine in Mexico. It has all 5 levels of control, controlling 15 primary fans, 12 airflow regulators, and all the associated flow, temperature, and gas monitoring. In this example, they're saving around 178,000 euros per year. Another example is the Glencore Nickel Rim South mine in Canada. That has also the 5 levels of control, controlling 5 primary fans, 199 auxiliary fans, and 21 airflow regulators with all their monitoring. Just an example, they have 5,550 horsepower just on the primary fans on the surface. Their main justification was to increase the production, to be able to manage their fleet, but they also were able to achieve significant energy savings. And here we have an example between 2.25 and 4.5 million euros savings per year. And we can also see the breakdown between the different fans, auxiliary fans, intake, exhaust fans. There was also heating reduction costs because of the airflow at the inlet could be reduced, and the peak energy costs were also significant in this example. Next example is the Newmont Eleanor mine in Canada. We have 5 levels of control, controlling 5 primary fans, 240 auxiliary fans, 41 airflow regulators, all the monitoring associated with them. They have 196 vehicles with RFID tracking. And they were able to achieve very significant yearly energy savings between 4 and 5 million euros per year. They were also last year awarded the Eureka Prize from the government for innovation with our ventilation on demand control system. Also, we can look at the costs of the energy, which is quite low. So we can see that you can achieve high energy savings, even with low cost. And we'll see some other examples where the energy cost is actually much higher, which could yield much more energy savings. So here we have an example of Dugald River mine in Australia, which has 3 levels of control, controlling 22 auxiliary fans, 24 regulators, all the associated monitoring. Howden provided all the automation panels here, and we've also provided the automated regulators for this project. Another example is the Fresnillo Saucito mine, which has 3 levels of control, controlling 20 primary fans, 3 regulators, the monitoring. Howden also supplied the hardware kits in this case, and we can see the energy cost is quite more than the previous examples that we saw. Fresnillo La Cienega mine has 3 levels of control, controlling 4 primary fans, 2 regulators, 1 door, all the monitoring. We also supplied the hardware kits in this example. The Barrick Cortez mine has 2 levels of control with 3 primary fans. Fresnillo mine has 2 levels of control with 10 primary fans. And the example of Glencore Fraser mine, we have 2 levels of control, controlling 107 automated fans. So as a summary, with Benson Control, you can increase the production by managing your assets. You can reduce energy by optimizing your fans, heating, cooling, and reducing peak electricity as well. You can improve safety. One of the main factors is improving the air quality. You can plan ahead for the mine life ventilation needs. You can log and trend all the important data. And now the clients can take control with SCADA for real-time control and optimization. So thank you for listening and watching. And if you have any additional questions, send them to vensim@howden.com, and it will be a pleasure for us to answer all the question needs.
Thanks very much, Pavel. That was excellent. It was really great to see all this energy saving capability being demonstrated, and obviously linked with the digitalization revolution that's going on in the mining industry, as well as everybody else, as well as everywhere else. So that's a real example of things in action.
Definitely. Thank you.
Yeah.
Thanks. And we can we'll ask Thomas Newman to join us and work with present the next presentation. Thomas is managing director of Artel Pro, and as I understand, has been working closely with Continental Conveying Solutions, and going to be talking about some of the technical innovation in conveying and bringing us up to speed with what's going on in that environment. Are you there, Thomas?
Yes, I'm here. I'm listening to you very carefully.
Okay. All right. Well, I'll hand over to you, Thomas, and we'll look forward to
yes. Thank you, Tim, for the introduction. Yeah, and I would like to share with you some information about the offer of Continental Conveying Solutions. I am talking about conveyors. I'm talking about conveyor transport, and of course about how to implement this most effective bulk transport technology into the processes by monitoring the real data. And I would like to share some information with you about a fleet management, like in a tire business, with a fleet management for conveyor belts. Starting with some slides about the company, and I will go through here quickly because we are late, and I think it's very, how to say, understandable what is written on the pictures. Yeah, that Continental is. Oops, where is the presentation? Tim, you can see the presentation. Oh yes, the presentation is back. Thank you. You can see that Continental Solutions is switching from the leading conveyor belt producer to a conveying solutions offer company, and for that they are connecting these pieces together. Yeah, the old belt manufacturing, together with some electronic components, together with some service solutions. They are presenting to the market now the smart solutions even for conveyor belts. Just some figures about the company with 1 billion euro turnover per year for this part of the business. And of course, Continental is offering for the whole process chain, starting with digging, with transporting, with storaging, and servicing any conveyor in a factory, in a mine, in an open pit mine, or in an underground mine. What is new? New is the view on the equipment, and the view is a 360 degrees view, and we are understanding under that we are offering, of course, the belts. We are offering the field service. We can offer service materials. We are engineering, we are helping to engineer the conveying line together with the OEMs, with end users and service providers. And of course, we have the equipment for monitor all the real data and the condition monitoring data. And we are offering smart services, and I will tell you a little bit more about that later on. What is important to have in mind? Important to have in mind is that if you are thinking about cost efficiency in mining, you have to understand that for transport, the share of transport costs can be very high and can reach up to 60%. And that's why it's very worth to think about the technology of transport. Very often you will find in the mine the truck transport. We are sure that the conveyor transport technology is more effective in the mine for heavy rock masses to transport, for bulks and stuff like this. And even in cases when you have very long conveyors, as on the left side visible, interesting. Even if you have very long conveyors and if you have steep angle conveying solutions in use, then you have the question, because these conveyors are the arteria of your mine, and you have to care about this arteria in order to keep running this conveyor over the year. And that's why it's very important to collect data and to use the condition monitoring systems offering by the belt companies and by the conveyor equipment companies. Continental is offering a system looking into the belt. It is able to look into the belt like an X-ray system, but here on the magnetic field-based system, and we can detect and we can evaluate the data, and we can recommend what to do for the most heavy problems can arise with the cords, as example, in the belt, with the splices in the belt. And we can detect as well belt rips, and that's why these three cases can be detected by very interesting and very, how to say, strong and stable working magnetic systems. These systems can be installed permanently, but as well can be installed like a mobile device, and we can do scans at the field, and you will get, in each case, for the permanent installed and for the mobile ones, you will get all information in what conditions is your belt running. This information is very clear written and very clear understandable, because you will see the degree of the problem, you will see where this problem raised up, and of course, when the problem was detected. Based on that, you can prepare yourself, you can prepare your service engineers, you can prepare your service provider with the top information about at which places they have to repair and at which places they have to check the situation of the belt. When we are going on, this is one process, one offer we can do for this predictive maintenance part. But in the same time, we are offering a very interesting solution based on the Continental Cloud. In use is already for the tire segment of Continental a fleet management software based on measuring the pressure in tires, checking the lifetime of the tires and stuff like this. And we are doing the same with the conveyor belts now. We have managed a software platform under the name of Canti Plus. And in this software tool, you can put all technical data in, you can put in your reports, your photos, your videos at a place, and you can exchange this information with all stakeholders. It means the supplier, the end user, the field engineer, and the service provider. All these stakeholders can get to this information. And of course, in this system, we are storing our informations coming out from the monitoring system as well. And of course, we can create reports and we can customize this platform as well, and integrate this platform into an existing automation system. Why we are doing so? I think this is as well understandable, because we would like to provide systems which make the process transparent. We are minimizing the total cost of ownership. You will have, as a customer, a better cash flow and reducing unexpected downtimes. Yeah, this is more or less the story about the conveyor transport, the monitoring solutions, and the fleet management for conveyor belts. And in the end, I would like to share with you some slides about the last projects, the last interesting projects. As example here, the project in Chile, where we have provided and delivered the most strongest conveyor belt in the world till now, with a length of approximately 14 kilometers. And you can see here as well, we have delivered monitoring systems as well for the condition monitoring of this very interesting and very demanded belt running in a tunnel under high inclination. Here you can see the team installed the belt, and one additional slide coming out of a very interesting vertical conveyor solutions we applied since 1 year ago. And you can see here that we are elevating approximately 200 tons per hour with a height of 300 meters. This is a very interesting figure, because until now we have delivered these vertical conveyors with a height of approximately 100 meters. Now we are reaching up to 700 meters with this vertical conveyor. And this conveyor was installed in Mexico now, and it is running well, running smoothly, and with very low energy consumption. You can transport this 200 and up to 2,000 tons per hour vertically out of your underground mine. Yes, this was my presentation. Thank you for listening. Thank you for your attention. And my name is Thomas Neumann, and I am presenting today the solutions of Continental conveyors.
Thank you very much, Thomas.
Belts.
That was really interesting, and great to see that the vertical lift technology is really coming on leaps and bounds as well. I think that's going to be a solution for a few operations.
Okay, thank you.
We have Andrew Bamber back. He's been able to rejoin, and so Andrew will be our last presentation of this session. Andrew, as I mentioned, is Managing Director of Barra Consulting, and Andrew's going to be talking about some of the European projects that Barra have been working on recently. Andrew, over to you.
Tim, thanks very much, and sorry for the technical difficulties earlier. It wasn't my intention to be the last person of the day, but there you are.
Okay, great.
And firstly, let me start by thanking Arthur and Irina for the opportunity to present. Really enjoy the forum, and interesting to be in an innovative online forum as well, and glad to present. So, Tim, as you mentioned, I'm just going to give a brief profile of the European projects in which we've been involved. Certainly not as technical a presentation as previous presenters in the session, but hopefully I can still, keep this interesting. Just a couple of thoughts about us. Who Barra is. We're a small bespoke engineering consultancy. In-house, we do mining process infrastructure, cost estimation, financial evaluation for projects. We don't do geology, but we do work with very, very good people who do that. We don't do tailings and earthworks, but again, we work with very, very good people who do those as well. By and large, all of the people in Barra are well-rounded engineers, operators. What I like to say is, we've all worked on various sides of the fence. So most of the Barra associates have worked on the owner's side, for instance. A lot of us have worked for engineering companies. Some of us have been solo flyers, solo consultants, and come back into the fold, as it were. So we can look at projects from a variety of points of view. We do work in Europe, Eurasia, Africa, and the Americas. We have offices in the UK. I'm in the UK office. We also have a South African office, and we just opened an office in the Americas. And we work across the commodities, specialize in base, precious, ferrometals. We do a little bit of work in evaporites, largely in the UK here. Specializations largely out of the South African office in underground mining, so shaft design, shaft services for deep shafts, hoisting, pumping, material handling, and mine design in those contexts. Metallurgy and my particular speciality is metallurgy and sensor-based sorting, and I'll talk a little bit about that in the slides. And we also again do infrastructure, underground and open pit. At the moment, 5 partners, 20 associates, and we are growing. So it's a good time to be in the business. Very high level view on European projects that we've been involved in, and I'll give some details on some of them, not all, with respect to the constraints of time. Salamanca uranium project in Spain that we did with our friends at CSA. For Expo, we were involved in very early days at Poltava on the bankable feasibility study, and also early stages of detailed mine planning there, and we're also still involved in resource and reserve updates, again together with our partners at AMS. Trelleborg Minerals Tin Man project in Czech. We worked extensively with Minico on their project in Bosnia and Olivo. I've got a slide on that. Scott Gold, Scotland's first and only gold mine, where we did the bankable feasibility study, the DFS, again together with our partners at CSA. We've done various things for Tethyan, due diligence on things that they've been looking at in the Balkans, things that they've been working on in the Balkans. Also Medigold, process options and inputs to their resource statement at Barge, again with our friends at AMS. Because of our location, I guess we work quite a lot with Bulby, ICL Potash in North Yorkshire, because our office is there. It makes it easy. We're also doing a bit of work for Schlumberger here in the UK, up in Scotland, mine design, ramp, geotechnics, etc. So I'm going to give a bit of a sense of some of those projects in a bit more detail, what we do and where we've added value. Very quickly, the Tin Man project, interesting for a couple of reasons, I guess. Smallish skarn-hosted tin deposit right on the border between Germany and the Czech Republic. So I guess if you walk down the added to the mine, you actually cross the border, which is quite interesting. Reportedly discovered by accident, as a few things in history, I guess, have been, by the USSR when they were looking for uranium. It was acquired from Inca in 2013 by Trelever. We worked on a bunch of concepts to look at the, I guess, optimal mining method and mine design in this narrow vein situation. We are still loosely involved. We're looking to do some more work on that in the coming periods. For Expo Poltava, very interesting project, I guess, of mine now. Massive iron ore deposit in Ukraine. There are over 1 billion tons reserves at 30% iron. It's a magnetite operation, so high grade iron ore, a sweetener for smelter feed for smelters in Europe and elsewhere. As I said earlier, we were involved in the bankable feasibility study in 2014. We were involved actually for a number of years in detailed mine planning, mostly for Yeristova pit, and we have been doing ongoing resource reserve audits for them along. In terms of the value that I think we brought here, as many of you have worked in the former Soviet republics will have discovered, there's often very, very good resource data available in the Soviet context, in those old classification contexts, A, B, C1 and C2. Often very well defined, but need some translation to get those to either JORC or 43101 compliance. So some very interesting work there. Olivo, right on the opposite end of the scale to Poltava. So very small, narrow vein, high grade lead mine, sericite. Before I got involved in this project, didn't really know what sericite was. Lead carbonate mineral, so very high grade lead, small mine. Actually, and also now the historically, I guess, the first new mining license to be awarded in the Balkans since the war. So historic for a number of reasons. Technically challenging, very, very small, but also, and we'll talk a little bit about this with Scott Gold. Very challenging from a mine design and a mine planning point of view, because of very high levels of short range variability. So very narrow, it's narrow vein, number one, very high variation in grades, but also in geometallurgical parameters as well, granularity, hardness, particle size distribution, etc. So very, very hard to essentially plan for a consistent feed for the plant, which was largely gravity and robust with respect to those things, but still needed careful design from a mine planning and production control point of view. Similar to Olivo, also in our sort of narrow vein underground mining speciality, we did work very early on with Scott Gold at Canonish. We're involved in the pre-feas, bankable feasibility study, as I said earlier, with together with CSA. Very interesting mine again. So volcanogenic intrusives into the Grampians, lead, zinc, gold, silver system. In like other mines, probably actually a lead zinc mine, but it's called a gold mine because it's easier to raise money for those, I guess. 250,000 ounces at 14 grams a ton. Mine development is ongoing, I guess somewhat delayed by the current COVID crisis, but looks like early June things have restarted and they will be in production on a delayed plan, but they will be in production very soon. Also, more recently, we've been involved with Medigold at Klemina Barja again with our partners at AMS. We're at resource statement stage now, but going into scoping study. Again, very interesting project. Large, thick, flat-lying gold system. Schisty, breccias, lots of variability within the zones, but zones are very well defined. I guess the challenge here is it's, you know, again, it's a gold project. There's lots of other things in here that make it challenging for conventional gold treatment routes. And so the value add I think we brought to this project is innovative process development to look at non-conventional offtake possibilities. And we're looking at Albion process here and potentially pressure oxidation and trying to trade off the two against each other. And with those options, this project then starts to look very interesting and quite prospective. So in conclusion, you know, as I said earlier, we're a small bespoke engineering consultancy, deep experience in Europe and the CIS, former Soviet republics. We're multidisciplinary, so again, in-house we have mining, process engineering, infrastructure, and we work on the geology side upstream of us with a number of partners and downstream in terms of tailings and environmental with others. And we have a largely value-driven approach, value for the client in terms of what value we can bring for projects, but also the value we bring in terms of just the scale and scope of study work that we need to do to get things to the next stage of development. So looking forward to more work in Europe and the CIS, and happy to field any questions.
Great, thank you very much, Andrew. And it's good that you were able to get the technology sorted and finish up for us. So that is the last presentation of this session. I'd like to thank all our speakers this afternoon, William Harding and Mike Di Giovanni, and Chris Bray, all from SRK, Andy Beveridge from Patterson and Cook, Pavel Bartak from Howden, Thomas Newman from Artel Pro, talking about conveyors there, and Andrew Bamber, who's just finished up from Barra Consulting. You know, clearly we've got quite a lot of expertise that's helping the industry, you know, build safer, more efficient mines, and the technology that's coming through, I think, is really quite astonishing, allowing us to really maximize the opportunities that there are available. So again, thank you very much. Thank you to Minex and to Arthur for arranging this event and allowing us to have these presentations and have these discussions. And I'll hand over to Arthur to wrap up for the day, but thank you very much.
Great. Thank you very much, Tim. Thank you very much for your kind words and also supporting Minex Europe Forum. You've been very consistent for the last 5 years, and I'm very glad that we could bring the forum online with support of SRK Consulting and Micromine. I would like to say thank you to all speakers. Thank you very much. You've been very, very patient.